We have Dr. Jeffrey Struik from Struik Solutions, and he's going to be speaking to you about vulnerability hunting with CHIPSEC and LuvOS.
All right, well, good morning, everyone. I usually like to start off with a really lame joke, so be prepared not to laugh. Who made King Arthur's table, round table? Circumference. So today, we're going to talk about CHIPSEC and LuvOS. So we're going to talk a little bit about what each of those are. I'm going to provide a demonstration. It was supposed to be live, but I had to do a screen capture of it, and then just a real quick conclusion. So the first question might be, why do we need something like CHIPSEC and LuvOS? Well, obviously, having a low-level hardware-level breach is nearly impossible to detect. And it would allow the attackers to basically gain irrevocable persistence to the machine. It could obviously cause the device to become useless. And there's devices everywhere now, and it just continues to expand thanks to the Internet of Things. And last but not least, it's a lot of fun to learn this stuff. So first we'll talk about CHIPSEC. So CHIPSEC is basically a Python and C-based tool that was developed by Intel. This tool is open source and it's available on GitHub. And so what it does is checks low-level settings, like at chip level, and different flash memory settings. It can be used, there's multiple ways that you can use CHIPSEC. CHIPSEC, it can be either installed on Windows or Linux. It is available and can be put onto a Mac, but there's a lot of additional risk if you do put it on a Mac. And it can just also be used as a standard. You can just build the Python library as a standalone Python executable. And probably the best option is the executable UEFI shell version, where it's basically in a pre-boot environment, and it prevents the possibility of damaging your runtime system. But we'll talk a little bit more about that in the following slides. So the basic structure of CHIPSEC is that there are two primary executables. One is the CHIPSEC main, and then the other is the CHIPSEC utilities. So each of those have specific functions that can be used. Whenever you do make or compile the CHIPSEC program, you have to build out the drivers for the OS helper, and that is something that has to be done specifically, obviously, for Windows and Linux or Mac as well. And it's important to note that when doing that, it will fail if you try to run it within Windows. Initially, it will fail because it will not pass the signature check for that driver. So if you want to test on a system, on a live system, without doing the USB boot, you need to set the boot configuration to not do the integrity checking, and then there's one other setting in there that you have to set, so that way it'll allow you to run unsigned drivers on there. And then there's the specific test modules, so you can see up here you've got the I/O, PCI, SPI, CMOS. There's also for UEFI, the BIOS, Secure Boot. All of those are different modules on there, and we'll see that during the demonstration. So the CHIPSEC main module is obviously the primary test used to run, and so what the main module does is it basically will run through every single one of the tests that comes with CHIPSEC. It is a pretty comprehensive test suite. It runs very quickly, but it does also provide you the capability to run a module by itself if you're not wanting to test everything, or say you have multiple failures that you've come across and you want to be able to investigate those further. You can then run that verbosely against those single modules to get a little bit more information. And it does allow for multiple output formats. Specifically, the two that it comes native as is JSON and then XML. And the JSON format can be just the basic pass-fail information, or you can also record the CHIPSEC session, and it'll dump basically the entire test into a JSON file. So that way you can run that test again to see if you have any changes to your platform or anything like that. So it does provide a lot of valuable information about any possible chip-level vulnerabilities. Like I said, the JSON and XML, and probably the most common thing that you'll see would be any misconfigurations in the board level memories. So it checks for, like, if you have the ability to write to like the Ethernet area, or if the flash hasn't been properly overwritten and leaves open memory space. So right here is just a real quick example of the BIOS keyboard buffer test. So you can see here that it's empty, all zeros, and basically that demonstrates that there's nothing left in the keyboard buffer. But there are, so my demonstration system, which I am unable to plug up, it had some stuff in the buffer, and so if you take the time and dig in, then you can obviously export that and see what was in the buffer. And so this would be important, obviously, if you were trying to discover like the BIOS password or something along those lines, to be able to execute the attack. Or it also holds like the secure boot passwords. If you're using password authentication for BitLocker or stuff like that, it will hold that information as well. So this was the just a real quick from a demo system, the S3 boot script, basically the resume from sleep, and it shows there that the memory is unprotected, and so it tells us right there what the module is, and that's valuable whenever you want to go and take an additional step into the test and discover if you can actually modify the memory at that location. And in this case, we'll get a little bit further into it. There's a utility script that you can run and prove that you are able to write to it. And so that's important, because you could then modify something during the resume where you can again capture credentials or additional information. So this was the kind of the explanation of what happens whenever you run the modification test. So you can see that it moved the terminate opcode to different memory locations, just as a demonstration that you were able to move stuff around in memory and write to the memory to show that it actually was not protected. And you do that obviously because in the case of that test, it showed it had failed initially, but it is possible that it detects a failure, and when you go to test it further, it will not be able to prove out because just a different setup in the system. So next is the CHIPSEC Utility. So the CHIPSEC Utility is a lot of fun. You can do a lot of really neat things with it, but it is very dangerous, primarily because it gives you direct access to the hardware, not just read access. So you can go in and modify things, and obviously you don't want to go and modify things that you're not 100% sure what they do, or you may end up with a really big paperweight. So you can do things specifically like dumping the memory into binary files or ROM files, and you can also dump the variables for like the UEFI settings, and similarly you can dump the key for the secure boot stuff, and get your primary key, your KEK, and some additional information there. So one of the commands is the PCI command, and the PCI command, it will allow you to basically have direct access to the PCI configuration registers. And through that you can obviously gain additional information, and you can modify memory if it's not properly written. The TPM command, it will allow you to enumerate various TPM variables, and you can dump that obviously as well, and use that dump for additional forensic analysis if necessary. And the ucode command, given some of the recent hardware attacks, it is valuable because it can provide you with the microcode ID for that CPU, and if it's been updated, stuff like that. So that way you know if certain vulnerabilities may apply to it. All right, the CHIPSEC demo. Let's see if it starts on its. Nope, it did not. All right, so I put some delays in there. So I'm basically dumping everything to that demo JSON file. So that's how fast it actually runs. It runs crazy fast, and you can't see anything here. But it failed the Spectre V2. Get to the next one real quick. Sorry. All right, so when I ran the common.cpu.spectre v2 module by itself, then I was able to get more information. Specifically, it provided me information that indirect branch restricted speculation is not a capability that was on that processor. And then it also tested at the OS level to see if there were any mitigations in place, which they did not have any mitigations in place. You can't really see the red. So it does, it does say that there may be additional solutions available, but it doesn't give you really any additional information to help with that. All right. So this was the SPI flash memory access. So you can see here that it says that you have access to the gigabit Ethernet region of the SPI flash. And so you can see right there that it does show it as having the read access, but it also shows it as having the write access. And so something like that is kind of important to pay attention to, because it is possible then that arbitrary code could be loaded into that area of the flash and executed, and you'd be able to gain some very low level persistence. Sorry, I thought the 5 seconds timing was enough to talk through, but it is not. So this is the secure boot variables access controls. One of the test systems that I had did not have that configured correctly. Specifically, it was a very old Lenovo that I had found lying around. And so the biggest thing is it's checking to make sure that some sort of authentication is required before you can write anything to those secure boot variables, and that's important for obvious reasons. And in this case, it has the time-based authentication. And so whenever you dig into that module, it basically will it'll give you a warning if it's not time-based authentication, but it still basically says that you're okay. But the best is the time-based authentication for the write access.
Where does it get its source of time? Is it if you have a real-time clock battery dies, that ruined?
Are you talking about
Time-based authentication.
So that would be, yeah, it would be at the chip level would be the source of time. So I honestly don't know the answer to that question. That's a very good question. I had not considered that before. So again, this is just showing that the keyboard buffer was empty. It does not necessarily mean that it is, but it definitely indicates there that it was more than likely an empty buffer. The resume. I'll let it go forward to the UEFI variables here. So right here with the UEFI variables, it basically is looking at the UEFI specification, and it has basically the database of what that should look like stored, and then it's testing each of the variables to make sure that the access controls are configured correctly. So the NV is non-volatile, the BS is boot time access, and then the RT is runtime access, and then time-based authentication, and then just authenticated right. So each of those, it tests each of those to make sure that they are configured in accordance with the UEFI specification. So that way you know that someone doesn't have access to certain variables and the ability to modify those variables. And for obvious reasons, you would want to make sure that they are set correctly. Otherwise, someone could definitely do some damage to the system. All right, and then this next, I'll just pause that real quick. So that what's about to run is the firmware test suite, and I just have that in there because we're going to be talking about it a little bit later. So I'll go ahead and run through that little segment, but then we'll expound on that a little bit later as far as what it all does. And so the firmware test suite, you can't see it, but it's the TAC-B command, and so it's a batch. So it's running the preset bunch of tests, and this is also similar to CHIPSEC, but it does do some additional testing, and it'll check things like fans and all of that different stuff, and the firmware test suite was developed by Canonical Ubuntu, and they have it also as a standalone live operating system, but we'll talk a little bit later that it's also included in the Linux UEFI validation of this. So you can see here it does take quite a while to run, and specifically when it gets to things like checking your computer, wake-up scripts and stuff like that, where it'll just sit there for a little bit. And when you're doing it on older machines, you definitely think that it freezes because it takes quite a while. It does. So, and you can, similarly with this one, you can have it dump out the output to a log file, so that way you can then take it offline and analyze it further. So just as a quick recap for the CHIPSEC side of it, it does have a wide range of pre-configured vulnerability checks. One thing to note is that you can make your own configuration files and develop your own scripts to check. If you have that understanding and that's something that you want to do, like whenever you go through the manual of the CHIPSEC, it does show some additional modules that they don't include, but it was modules basically to prove out some of the vulnerabilities, and it was showing how you could steal passwords and different things like that. So they had written their own modules kind of for their own demonstration purposes. I have not taken the time to do that yet, but so it does work with Mac, Linux, and Windows, as we talked about. But obviously, in my opinion, the best is doing the custom UEFI shell because it reduces the overall complexity and the risk to the system because you're able to, yeah.
They have like Grub or like a BIOS-based shell instead of UEFI?
So theirs, the short answer is theirs is no. However, so I had to make this for someone, and they had the restriction that it had to be able to be both, legacy and UEFI boot, and it had to be compatible with their current Windows system. So I just took a Windows PE and then loaded it in there, which doing it that way is kind of a pain in the butt, but it worked. And it was something that's easier for, like, if you're doing this in large scale, right? If you're trying to do this on a network of devices and you just set it up to Pixie boot all of them, it can run all of those. You can make your script. It'll run all of those, and then if you wanted to set up to have it push back to a share or something like that. In the case of why I did that, that's what I had to do. So it would just run the script, collect everything, and then pull it back off and dump it onto this one central computer. So that way, the goal was to check all of these identical pieces of hardware that all came from the same manufacturer to make sure that that what they were saying was actually true regarding the memory configuration. Yeah.
How compatible is this with Intel's SGX? So you mentioned the key encryption key, so that's why.
Yes. So it does check for the presence of SGX. So I know it works with it. I haven't done much with the SGX side of the house, but I know it does do the detection, and there are some additional utility scripts that you can do some additional checking with. And last, it is very powerful. You definitely want to use it with caution, specifically the CHIPSEC Utility. So next is the Linux UEFI Validation OS. So kind of similar to CHIPSEC. It is also an open source project. It's backed by Intel. It is a live operating system, and it really is kind of what I would consider a Swiss Army knife of doing the low-level testing. And one of the big benefits is that it does provide a nice packaged report, as opposed to CHIPSEC, where it just dumps like an XML or a JSON file. Whenever you run this, it creates an HTML and has a directory of all the results, so it's just easy to navigate and comb through the results. So the LuvOS has several more tools. The BIOS implementation test suite, so that one is kind of the structure of LuvOS is, and that one is also UEFI only. It'll run bits first when it's loading, and then has a script in that bits UEFI or that bits EFI file, and points to the LuvOS EFI file to continue. It does have the firmware test suite, as we talked about. It also has the NDCTL. So that tool by itself is also a very powerful tool for managing non-volatile memory for the kernel subsystem, and so by itself you can do things like erase, create memory space. So it's something that you want to be very careful with. I've never been brave enough to try to do anything with it as far as doing any creating or destroying of space, because I don't have a big enough budget to be able to afford breaking my computers. And then there's the Kernel EFI Warnings. So the Kernel EFI Warnings is basically a shell script that the folks at Intel made, and it'll check your dmessage bus to see if there's anything that, any kernel messages that might provide indication of compromise or vulnerabilities within the UEFI or system. And then the pstore test, that's specific obviously to Linux, and it's just designed to record the data whenever there's a kernel crash. And then CHIPSEC, which we've spoken about already. So it is developed as, or it basically leverages the Yocto project. There are the 3 basic configurations, and it does support both 32 and 64-bit. The USB boot is the easiest. NetBoot is very nice for the situation of if you're wanting to do a network-based PXE testing. The challenge, I will tell you, with NetBoot is you have to do some customizations to the LuvOS itself, and they provide you good instructions. In saying that, I've not been able to get their instructions to work as they have suggested. So it's there. I'm sure it's doable. I just haven't been able to dedicate the time to figure out what I'm doing wrong. And so basically, the NetBoot is nice, obviously, for the PXE, and it'll basically write results. If you have a web server, you just create this little upload PHP file, and it points to that and pulls everything down. That's the idea behind it. So talking through the tools a little bit, the bits, it allows for checking of microcode. It does support Python scripting if you want to add additional testing. And LuvOS uses scripts to execute the bits test. And you can run it from Grub as well. So you're not just limited to only running it in LuvOS. And it uses Python for the execution. So this is just a screen capture, or a picture of the screen rather, showing bits in execution, and this is what it would look like if you ran it initially. Whenever you were booting up LuvOS, you'd get this screen, it would spit out all the information about the tests, and then it would carry on to finish booting LuvOS. Firmware test suite, I had run that during the video there, and this is an example of the firmware test suite, LuvOS by itself, and you can at that level, when you run the firmware test suite by itself, you can select individual tests to run or run all of them. One of the challenges, especially with the more modern OSs, and depending on how you have the system configured, is it wants to do a reboot test if you tell it to run all tests. So it takes a very long time, and if you obviously don't have your system set to boot in the order that you want, if you just do a one-time override, then it's not going to be able to continue on the test. It'll reboot, and if you don't catch it, it'll just carry on booting the OS. So there are a bunch of tests that you can run with the firmware test suite, and honestly, you also within the LuvOS, if you decide to build it yourself, you can. It uses BitBake since it is Yocto, and you can go in and modify the recipes for the firmware test suite if you wanted to have it run different tests. It just would require you to then compile everything yourself. And it does support, or it does identify BIOS, UEFI, and ACPI errors. There's over 50 different tests, and it can execute either within Linux, the LuvOS by itself, or LuvOS. And there are some overlaps with CHIPSEC, which from the verification standpoint is very nice, because instead of relying just on the CHIPSEC or just on firmware test suite, that you are able to then do that comparison and validate is that vulnerability an actual vulnerability, or was it just one that popped up as a false positive? So the Kernel EFI Warnings, like I said, it's a shell script. It just analyzes the message buffer, and it will look for kernel messages that may indicate a UEFI flaw. So the MD-CTL, like we talked about, you can create and destroy the namespace and do other memory configuration. Obviously, it is a very powerful tool if you run it by yourself or by itself and start tinkering around with that stuff. But the LuvOS basically is just using it. They have scripts built in that check the security configuration of the non-volatile DIM, and so that's like I said, I've not been brave enough to try to do any of the creating and destroying of namespaces myself, but it definitely seems like it's a great tool to check configuration of that. Okay, so this is just basically the screen that pops up when it's executing. It just gives you a very basic screen, and then tells you what test is running. And then when it's finished, it'll tell you basically how many tests ran. So in this case, it ran 7, and it had 170 unit tests, of which 97 passed, 28 failed, and 54 were skipped. And there were also 11 warnings. And so in this case, this was from the USB boot. And so whenever you write the LuvOS, it will have the LuvOS partition on the USB, but then it'll also write a persistent partition to write all the information to. Yes?
So if you choose like kernel parameters, like debug, does it actually show the
Yes.
execution?
Yep. Yep, and that's one thing that I didn't mention about the net boot. You can set it up so that way you can basically do a netcat when it's running and get the outputs that way as well. Again, it's something that is possible. I have not been fortunate enough to figure it out yet. So. All right, so I went a little bit faster than I should have, I guess. Kind of wrapping things up, there's, obviously we have computer chips and everything. Even though this set of tests is really specific to Intel, there's an obvious importance in testing firmware and testing that low level memory of devices. Since if it's not configured correctly, you can gain a great deal of resistance. CHIPSEC, which we first talked about, is a very, very, very powerful tool. You can break your device, and that's something that you clearly don't want to do. And you can leverage those utility scripts to dig deeper. If I would have known I had a little extra time, I would have gone through some of those utility scripts to show how you can dump that information and just gain a little bit more information about the system. And then LuvOS, it does provide a great deal of tools to test your system at the hardware level. It can be used to pixie boot, which is very nice if you're doing it obviously on like a production line or something like that, or if you're just trying to do the testing in a more efficient manner, so that way you don't have to go around and plug a USB stick into every computer that you're testing. And it does provide a very nice report of the findings in an HTML format. Any questions? Going once? Going twice? All right, thank you guys.